This is Algebra 2, Chapter 7, Section 6. We've been talking about exponential functions and even the log function, and now we're going to introduce what we call the natural base e. E is a constant that is very helpful when calculating interest. We're going to show you that in one of the later examples. And the way we're going to start with the introduction of this function, or excuse me, this constant, is we're going to actually put it into a function and graph it. So the problem here, example 1, asks us to graph e to the x minus 2 and all of that plus 1. So you have to be very careful when you type this in your calculator. So let's make a table by pulling up the graphing calculator. If you have your graphing calculator home, please pull it out now. So you'll see here we have the log function and then 10 to the x. Remember we talked about how those were inverses. Now we're going to talk about the natural log, that's what this ln stands for, and e to the x. E to the x and natural log are inverse functions. So when you're calling up e to the x, you're going to type in your y equals, and you're going to hit second natural log, which pulls up e to the x, and you should type in this, e caret x minus 2. Then make sure your cursor goes down to the bottom level again and then hit plus 1. When you make a table, you're going to notice that e, since it's irrational, is going to give us values that aren't whole numbers. Since e is kind of like pi, we can reference pi. You know what pi is. It's 3.14 many more infinite infinite number of decimal places. And e is the same way. E has too many decimal places for us to write out, and when we plug it into our calculator, it gives us not whole numbers, irrational numbers. So our table of values looks like this. Remember, you can use second graph to call up your table of values. Your numbers should look like this. When we graph these points, -2, 1, -1, 1, etc., since our y values go from 1 to 9, you can make your axis such that it looks like this. Our y values go pretty much from 0 up to 8.4, and our x values go from -2 to 6. So we can plug each of these points in. -2, 1, -1, 1, 0, 1.1, +1, 1.4, 2, 2, 3, 3.7, and then our 4 value actually ends up off the graph, so we end with an arrow. So as you see, the natural base e is an exponential function. It has the shape of an exponential function. This particular graph has an asymptote, or a wall, at y equals 1, of y equals 1. So the range for this function would be all values greater than or equal to 1, because 1 is actually one of the values. And you'll see that makes sense. We took the natural base e function and we moved it up 1. So the wall's right here at 1. The domain for this function, since it has arrows on either side, all values of x, so we'd say all real numbers. Example 2 has an a, a b, and a c. And what we're going to do now is we're going to actually apply the fact that the natural log and the natural base e are inverse functions. So just like when we had log and the little b and the big B matched and we were able to undo each other and just get what was there, we're going to do that same thing with these functions. So let's start with example A. Example A says, and this does not say n, it says natural log. So little l, little n stands for natural log, even though on your calculator it's a capital L and a capital N. Natural log of e to the 0.15t. So because we're simplifying, we're not actually solving this time, we're going to write the natural log of e to the 0.15t, and these two cancel each other, so we just get 0.15t, and that's the answer. Looking at this one here, we almost have e raised to the natural log of something, but this 3 is in the way. So we need to move the 3, applying the exponent rule or the power rule. The natural log and regular log have the same rules. Okay? So in A, we applied the inverse property, In B, we're going to apply the power property. We're going to move the 3 to the back here. Our first step is going to be e to the natural log, parentheses x plus 1 cubed, or raised to the third. And all we did was move this 3 to the back. Now we have an inverse, e to the natural log, or the natural log of e. Because these undo each other, we get x plus 1 quantity cubed. And that's the answer. Again, not solving, just simplifying based off the directions. Okay, example 2c. We see a natural log of e to the 2x. You should practice reading these out loud. The natural log of e to the 2x plus the natural log of e to the x. We can simplify each of these because they're both inverses. This part becomes a 2x, and this part becomes an x. So we get 2x plus x. When we simplify that, it's just back to Algebra 1, combine like terms. The answer is 3x. Okay, on your handout, you should notice all of this printed information here. I'm going to kind of walk through this quickly. We'll practice it more in class tomorrow. I just want to get you to get this copied down kind of quick. Example 3 is an economics application. Some of you may have seen this equation before if you've taken business. Our final amount is equal to the beginning amount. It's labeled P because it's usually called principal. And we use E, this function E, this constant E, as raised to the rate times the time. And what we do is we take the given information from the problem. So you should take your handout and maybe underline 500. That's obviously the beginning amount, P. The 5.25% is our rate. We're going to change that to a decimal. By moving the decimal back 2 places. And the 40 years is obviously going to be plugged in for T. All of that is spelled out for you in this first written instructions here. Substitute 500 for P, 0.0525 for the rate, and 40 for the time. When we do that, it looks like this. A equals 500 times E raised to the parentheses 0.0525 times 40. We're going to use the E to the X button on our calculator. When you plug it in, it should look like this. 500, then we're going to hit second natural log. That's going to bring up this E. Then we're going to hit caret. Make sure it's raised to the 0.0525 times 40, all in parentheses. Okay, don't forget the parentheses, and our final answer is 4083.08, blah, blah, blah. But because this is a financial question asking us for a total amount, we're going to put that our final amount is $4,083.08. And we can write it even better than that by putting the total amount is $4,083.08 with the number sign. Okay, over to the science application problem, example 4. Example 4 is talking about an element, plutonium-239. Plutonium-239 is just the name of the element. This 239 has nothing to do with the problem. I want you to underline this word, half-life, that's hyphenated here. And then after you underline it, I want you to draw an arrow to this box on your handout, because when you see half-life, you're going to use this equation. Just like on this side, when you see compounded continuously, underline that, put an arrow to this one. I need for you to know which word problem involves which equation. So using this equation, it looks kind of funny. We're going to have a final amount, a beginning amount, just like with this equation. But this is saying what is the amount of the substance at 0 time. And this is saying what is the final amount of the substance. The E is just a constant, the natural base E we've been talking about. And the K here is called the decay constant. It's how fast does this particular element decay. So the K constant, K, is what they're asking us to find in step 1. Well, since this is our unknown, E is not a variable, remember, it's just a number. The T that they gave us in the problem is 24,110, so we're going to plug that in right behind the K. The end amount is just half. Any half-life problem starts off this way. You put a half there equals the beginning amount of 1. No matter what our sample size is, we're going to end with half that much. So this is the way the equation looks. 1/2 equals 1 times e to the minus k, parentheses 24,110. The next step here, you can read in your handout, is to simplify and take the natural log of both sides. So I'm going to write out the natural log in front of both of these. Remember, we're trying to get to a variable that's in the exponent for e. And we know, let me go back a little bit here. We know that taking the natural log of e will get rid of the e. So we're trying to get to this variable. We put the 24,110 in front of k. We leave the negative. We can't get rid of that just yet. And now we have the natural log of 1/2. So realizing that 1/2 can be written as 2 to the negative 1, we're going to take the natural log of 2 to the negative 1 and then set that equal to what this simplifies to. This is an inverse, so it just simplifies to the negative 24, 1010k. The next thing we're going to do is we're going to simplify the natural log of 2 to the minus 1. We're going to bring that negative 1 to the front, applying the power property. Putting that negative 1 in front of the natural log of 2 just gives us negative natural log of 2. This is just a number in your calculator, negative natural log of 2. If we're going to get k by itself, we're going to divide by negative 24,110. Plugging this into your calculator, the negatives cancel. We get approximately 0.000000029. Sometimes you'll get very small numbers in this step. Okay, for step 2, I'm just going to have you write this down. Go ahead and pause the video and write it down if you need to. I'm almost out of time, so we will go over these steps tomorrow. Get it copied down, and I will see you tomorrow.